Okay, so let's go ahead, and you said you got problem 1, correct?
Yeah.
Yeah.
Okay. All right, so what we have is a rectangular beam, and they give you the cross section on it. Okay, so let's draw the cross section. And since it's rectangular, we're going to assume, because there's nothing else that would change that, that the neutral axis is right in the middle. Everybody okay with that?
Yeah.
So let me put the information for that. Let's see, we have, what is it? It's 10 inches wide. And 18 inches deep. So that makes it 9 and 9 above the neutral axis, correct? And it has an applied bending moment. It has an applied bending moment due to whatever the load is, which we know nothing about the load, of 120 kip feet. Okay? So they want you to calculate the maximum tensile and compression of the bending stress, and also 3 inches above the neutral axis. So where would the maximum information occur? Bending stress is equal to MC over I. So where's the maximum point of bending stress, compression, or tension in this cross section? What's it at the neutral axis? Nobody can tell me? What is C in this equation? Nobody can tell me what C references? Max?
I forget, to be honest.
It's the distance from the neutral axis to wherever you're determining where the stress occurs.
Okay.
So if you're at the neutral axis, what is C?
Should be 4.5.
It should be 0.
Oh, it's 0?
If that's 0, this goes to 0. So there's no stress at the neutral axis.
Oh, okay.
So where's the maximum? It's going to be out here.
Yeah.
It's going to be out here, right? You agree?
Yeah.
Okay, so because if C goes from 0 to whatever this is, it's just going to progressively get more stress as you go from here out. And the maximum point is going to be at the edge fiber, okay? Now, when you talk about shear stress, it's reverse. Shear is 0 at the edge fiber and it's max at the neutral axis, okay? So keep that in mind, guys, all right? All right, so let me erase this real quick and we'll go ahead and calculate this. So the statement of the problem is they want you to solve the maximum compression and tension, okay? Assuming that this force is coming down like this. We don't know that, but let's assume that the applied direction was straight down. Then we probably have compression at the top and tension at the bottom, okay? But we don't really know that. But we do know that we want to solve the maximum condition, okay? So that means that C is going to be what for a maximum condition? What did we just say? The distance from the neutral axis out to the edge fiber. So what's this distance going to be? Your total depth is 18. So what's this going to be?
9.
9. Okay. And because it's 9 in both directions, tension will be equal to compression. You agree with that now?
Yeah.
Okay. So we need to solve this equation. Bending stress is equal to M times C over I. All right. So we know M, we know C. We just need to solve what?
I.
I. Okay. That's pretty simple for a rectangle, right? 1/12 the base. In this case, the base is parallel with the neutral axis. So that's 10 times the height cubed, which is 18, divided by 12. Okay, so let's plug those numbers in. We get 18 cubed times 10 divided by 12. You guys let me know what you get, or you check me. 4860 inches to the fourth. Before we go on, you guys get that?
Yeah, I got that.
Okay, so we can just plug this in, right? So the maximum bending stress is going to occur with the moment. The moment is 120 kip feet, but we got a unit mismatch because this is going to be in inches and this is inches to the fourth. So we need that in what? We don't want kip feet. We want kip what?
Inches.
Kip inches. So how do we convert that to kip inches?
Divide by 12.
Let's be careful. 120 kip feet times 12 inches per foot. So we don't divide by 12, we what?
Oh, multiply by 12.
All right, that makes a huge difference. Okay, you would have been out by a factor of 12 the wrong way, okay? So we're gonna multiply this by 12. Whoops. Multiply that by 12. So what is C? For the maximum condition, we said it's what? 9, right? Divided by moment of inertia. Okay, so let's solve that and see what we come up with. You guys may need to check me. I'm not sure what I got here. All right, I got mine. 2.67 KSI. That's what I came up with. Did anybody get that?
Yeah, I did.
Unit okay? We agree with KSI?
Yep.
Okay, so they wanted to know max. This is max for compression and tension because assuming compression is here and tension is here, it's the same number. So this would be true for compression or tension. Okay? We okay with that?
Yeah.
Then they want to know what is the stress 3 inches above the neutral axis or 3 inches below it. So this equation just simply would become 120 times 12 times 3 divided by moment of inertia. And what we'll see is it's going to diminish. So if we take 120 times 12 times 3 divided by 4860, it looks like it's about 0.89 KSI. All right. Is that what you guys are getting?
Can you explain where that 12 came from?
The 12 here,
Yeah, I'm a little thrown off by that.
that's a conversion factor to get you from kip feet to kip inches. So
Oh, okay.
if we look at this, Mitch, there's 120 given kip feet, right?
Yeah.
But if we do that, our units would be all fouled up here, okay?
So it
So,
would just be in the wrong units and you just convert it over.
well, it'd be more than wrong units because you would have kip feet per inch squared or something goofy, okay? So it would be really just messed up. So
Okay,
all I'm
gotcha.
doing here is I'm saying I can convert feet to inches because I know that there's 12 inches, right? Per 1 foot. Feet cancel. So you could do this before you plug it in if you'd like to. It doesn't matter. A lot of times I'll just do it this way because it's easier to just put it in. But this would be equivalent to 100 and or 1,440 kip inches. So you could plug that directly in and not put the 12 up there. It just depends on
then
how you
just
want to.
Divide that by the 4860
Yeah. Well, times C.
times C, yeah.
Yeah. So that would be if you took that times 3 divided by 4860, you're going to get the same number. I'm just doing this all in one shot here instead of doing it separate.
Okay, I got it.
You do it whatever works best for you, okay? That's fine by me. Is there anybody else questions? Does that answer the question on that problem then?
Yeah.
Okay, so let's look at something. Now I said that we go from maximum at the edge to 0. So if you drew a cross section of what's happening to your stress and you plotted it out, what you would see is this. Hold on a minute. If I look at a cross section on this beam and I draw my neutral axis in there. Now I'm looking I'm not looking down on this like we are in this view. It's a little different view, okay? What I'm going to do is plot the stress though. So if this is the neutral axis running through that beam, what we have going on is a linear relationship. We're going from 0 to max and 0 to max. So what's happening here, this is compression, 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 and this is tension, tension, tension. So let me draw these little arrows in here. Get rid of this. So I've got, that's compression, compression, compressive stress. This is tension, tension, and tension. So the max would be 267 compression and 267 tension. And notice it goes to 0 and then it goes back up. And this is linear. So if you know the maximum and you know this distance, you could solve any value of stress that you needed to because you have a linear relationship. Okay. Are you guys seeing that? When we get to combined stresses, this isn't going to work that way, okay? It'll be different because what will happen is this thing will shift above or below the neutral axis, so it won't be the same numbers. In other words, the top fiber and the bottom fiber of your beam won't have the same values. When you have a homogeneous shape and you have, or material and you have a equal, like a rectangle, then this works out really well. Okay, is everybody okay with that?
Yeah.
Okay. What else would we like to take a look at? I'm going to go ahead and clean this screen up. And what other problems? Did quite a few of these in class the other day, I believe.
Yeah, I was looking at that. I think I'm pretty good with chapter 12.
Okay. Well, now we also did shear, and shear's a little different. And so was there anything in that? We did a couple of shear problems, but we didn't do a bunch. Would you like to look at any of those? Let's do problem 33, okay? You guys want to look at 33 with me?
Yeah, that's fine.
Okay. So 33 is on page 420, and it's going to reference us to another diagram, so we're going to have to look at that, okay? So I'm just going to do half of 33, and then I'll let you do the other half. So it says, using a framing plan with the loads given in exercise 18, calculate the maximum shear stress for a typical 2x10 joist for both the 12-inch and the 16-inch spacing. So we're going to do the 12-inch spacing first, okay? And then I'll let you guys do the 16-inch spacing later. Okay, does that sound good? This will kind of help you with the deck project, actually. All right, so if we look back on 18 for that, we've got a 2x12 joist. So we have a 12-inch spacing, notice on 18, and then they have we have a 16. Let's do that. Tell you what, let's do the 16 on center. I'll let you guys do the 12. So we'll do the 16 on center. Okay, so I'm going to draw a beam, a representation, which is just our joist. So there's my joist, and I'm going to have to, in this problem, we're looking to calculate maximum shear stress. Okay, so what kind of board is this? This is a joist. It's what? It's a 2x10, right? Oops. So we have a 2x10. And the 16 on center have a span of 12.5 feet. Now I'm getting that information from page 418, okay? Is everybody okay with that? We also have a load on this. So the load is given as 60 pounds per square foot. Okay, so we have 60 pounds per square foot. All right, so if you look at that framing plan, let me draw a picture of that. I'm just not going to draw, I'm not going to draw the whole thing. But you have a joist, and then another 16 inches, you have a joist, and you have another joist, another 16 inches. So it's 12.5 foot of span, and we have 16 inches on center. Okay, so what's the tributary area of this joist right here?
Is it 16 inches?
It is, because it's each joist is going to be responsible for half, right?
Yeah.
So each joist is going to be responsible for half the load. So there's your tributary area for that joist, okay? So it's going to be 16 inches times 12.5 feet times a load of 60 pounds per square foot. That's going to give me the load, okay? So the area is 16 inches times 12.5 feet. So the area, let me clean this up a little bit so we can see what we're doing. Get rid of this. So the load on this beam, the load rate, okay, the load rate that we're going to have on this beam is going to be 16 inches, but we want to convert that to feet. So 16 divided by 12 times a span of 12.5 times a load rate of 60. Okay, so if that's pounds per square foot, and this is going to be square feet, we're going to get this into just pounds, okay? So let's go ahead and divide that out, or multiply that. So what do we get? So we have 16 divided by 12 times 12.5 times 60. That's supposed to be 12.5 there, guys. Okay. Let me clean that up so you can see that better. Let's see. I had the 12 and okay, so that's 16, that's the area width in feet times the span times the load rate. And what does this give me? How much actual load is that joist carrying? I get 1,000 pounds. Okay. Is everybody okay with that? This is just like the deck project. Anybody out there?
Seeing the work itself is definitely a lot more reassuring knowing that I might have done this right.
Okay, all right. So if this is the load, actually this is not the load rate, this is the load. The load rate, you have to assume that this thing would be acting uniformly like this across it. So this is a uniformly distributed load. So if we know that that joist is carrying 1,000 pounds, the load rate is going to be distributed over 12.5. So the load rate is actually going to be 1,000 divided by 12.5. And that gives me 80 pounds. It's distributed out as 80 pounds per foot, okay? So this load rate is 80 pounds per foot, okay? So now what they want to know on this problem is what is the maximum shear on this joist? What's the shear stress, okay? In order to do that, we have to produce a shear diagram. We don't need a moment diagram because they're not looking for bending, but we do need a shear diagram. So assuming that this is supported on two ends like that, okay, which is a pretty good assumption, we would have a reaction here and a reaction here, okay? Everybody agree with that? And our distance is 12.5 feet. So we need to solve this reaction and we need to solve that reaction, okay? So anybody know what those reactions are going to be? Or can we calculate them pretty easily? Well, we have a uniform load rate of 80 pounds per foot coming down on this. So what we could remodel that as just a 1,000 pound load coming right in the middle. Correct? If you have 1,000 pounds acting right in the middle, what would be true about each one of these reactions?
They would both equal 1,000.
No, They would both equal half of that.
Half of it, right?
You're close. You're really close, right? If this is 1,000, Stacy, right? And it's right in the middle, each one of those is going to be acting a half. And you could take a moment and prove that, okay? Are
Yeah,
you
I
okay?
meant like the sum of them, like the sum of both of them would equal like.
Yeah, the sum of both of them would have to
Yeah,
equal
that's what I
1,000.
meant to say.
Yeah, yeah. So if you wrote, if we called this A, right, and we called this B, we could do a sum of forces in Y. Yeah, if you're saying that, that's correct. You could say that your reaction at A plus your reaction at B has to be equal to 1,000. Since it's symmetrically loaded, those have to be equal. But you could take a moment. If we took a moment at A, if you weren't sure about this, take a moment. That would prove it. So if I went over half of the distance, so that would be 12.5 divided by 2. That would be 6.25 times 1,000 plus, or actually this would be plus. This would be a plus moment minus 12.5 RB. When we solve this moment, what are we going to get? We get RB is equal to 6,250 minus divided by 1250 minus, and it gives us 500. So if you're not sure that you can do that by symmetry, you can always just take a moment and prove it. Okay, so we know that this is 500. And like I said, this is exactly what you should have been doing on your deck project to this point. So if you did this and it looks similar, you're in good shape. So this is 500 pounds, and this is 500 pounds. All right, so we need to, I'm going to clean this. Whoop. That's not what I want to do. Hold on a minute. Clicking too many things here. Let me clean this up here. Okay, so we need to construct a shear diagram. So how do we do that? You guys should be able to do this pretty well. What do we need to do a shear diagram? We need a critical line, right? We need another critical line. Are there any other critical lines on this diagram?
No.
Correct, right? Not right now, okay? You might have some develop, but not for what we've got going on. So you're absolutely right. So I'm gonna put my zero axis line. So this is gonna be my zero shear line. Now again, because we're not solving moment in there, we don't need a moment diagram, just the shear. Okay, so what's true about when we start out over here? What's happening? The shear is starting out here and it's going to what? 500, right? 500 pounds of shear at the reaction, correct? As you step across this beam, what's it doing? Staying constant or dropping? What are these guys doing? Down, 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 down. Agreed?
So then it's constant.
No. No, it's not constant would be this.
Or no, it's going down. Never
Yeah.
mind. Yeah.
It's going down at a constant rate, though. I'll buy that. Okay. I'll go with you on that one. How's that sound?
Yeah.
It's going down at a constant 80 pounds per foot. So if we
Right.
take 12.5 times 80, that would give us a negative 1,000. So what's happening as we go from one side of the beam to the other, we're going from 500 down to what? A negative 500. So there's your constant. And then this brings us back up. So this is negative 500. Whoops. Let me undo that. So this is negative 500 of shear. So we have maximum shear occurring where?
500.
Yes. And it's at, well, you gave me the value. I didn't ask you the value. I asked you where it occurred. Where does it occur? It occurs at the two reactions. Okay?
Oh, okay.
Yeah, that's fine. No problem. All right. So now we also have something going on here. What's happening here where it crosses? In terms of shear, you've got what going on there? It's going from 500 to what? 0. So there's no shear going on in the middle of the beam. No shear stress developed, okay? But we have maximum shear occurring at the two reactions. But what is happening at that point of 0 shear? This would be a point of maximum moment, okay? But we don't care about moment for this problem. We just want to know what is the shear stress, okay? Is everybody okay with that?
Yeah.
So what's the equation for shear stress? There's actually two equations we can use. If you're not sure, look it up. We're looking for this guy. Shear stress. Look on page 413. What do you see there for shear? VQ over IB. Does anybody see that? Page 413. Anybody out there?
You said 413.
Page 413. You seen that?
Yeah.
Okay. There's another equation right below it that says what? 3V over 2A.
Yeah.
Are they the same? Can we
I
do
mean,
this? Can we say
yeah.
this?
Yeah.
Why? This doesn't always work, by the way. But in this case, these are equal. Why is that?
500 plus 500 minus. I don't know.
Because it's a rectangular cross section.
Okay.
If this is a rectangular cross section, you can always use this guy right here. But if it's non-rectangular, you're going to have to use this. Okay. All right. So we're gonna solve it both with both equations. Okay, just to show you that they both work. All right. So we have a 2 by. So let me erase that real quick. We have a 2 by 12. What is it? A 2 by 10? 2 by 12. Let me look it up. Hold on a sec. I have it written down there, but I want to. All right, we have a 2 by 10. So we need to go get information on that 2 by 10 because that cross section is not actually 2 by 10. Does everybody agree with that? Dressed lumber is not going to be 2 inches by 10 inches. So where do we find that information? We did that last week. Where do you find timber information? Let's look under Appendix D on page 644. Appendix D, page 644. Anybody see a 2x10, what the actual dimension is? Looks like 1.5. 1.5 inches by 9.25 inches. Are you guys seeing where I'm getting that information? Appendix D, table D1. You can tell me what the area of that section is. It's on the chart. And the moment of inertia. Irvin, can you find that for me?
Yeah.
Is it 2.602?
For which, what are we looking at?
Moment of inertia.
What'd you get? 2 point what?
Oh wait, I'm looking at YY.
Yeah, okay.
98.93.
I don't get either one of those. Are you on appendix, you in table D1?
Yeah.
You're looking at, oh, wait a minute. 90, what'd you say?
98.93.
Okay, I agree with that. 98.93. All right. What about the area?
13.88.
Okay, 1388. And that's inches squared?
Yeah.
Okay. So we're going to look at two methods of solving this, okay, and show you that we should get the same number more or less, okay? So let's do the first one, the easy one first. Shear is, we said, could be equal to, what did we say, 3A? 3A over 2V, or what, 3V over 2A, right? You guys tell me. 3V over 2A. 3V over 2A. So 3, what is V? V is your shear, and that would be your max shear. 500 pounds divided by 2 times area, which we just looked up in the chart. Okay, let's see what that is. I get, you guys check this, I get 54.0 basically PSI. You get 54 PSI? Anybody get that number?
Yeah, that's what I got.
Okay, so let's do this the other method. It's a little bit more involved. We have to use there's my neutral axis. We have to solve, first off, we're going to have to solve Q, that static moment of area. So Q is this area right here times the centroidal distance from the neutral axis to the centroid, okay? So the area of that would be 1.5 times this distance, which would be half of 9 1/4. Everybody get this area? 1 1/2 times half of 9 1/4, right? What would this distance D here be? The distance from the neutral axis to the centroid of that rectangle. What would that distance be? Well, the centroid is going to be what? Half of this distance, right? The centroidal y value would be half of that distance. So if this distance is half of 9 1/4, this distance is going to be half of 9 1/4. So what I'm coming up, you guys check this.
2.31.
Say that again.
2.31.
I get 4.625.
Oh, okay. I have.
Wait a
the
minute.
4.
No, I might be wrong. Hold on a minute. Hold on a minute. I think you're right. I think I didn't do it. 2.3?
Yeah,
Let me just check
2.31.
that. Yeah, I was wrong. My 4.6 was the total half, right?
Yeah.
So let me, you're right. Absolutely. Thank you. So let me erase this. Okay, so yeah, we have half of that 9 and half of the 9 1/4. How's that sound? Or a quarter of it, right? So let's see. Oh, come on. Shut that down. No. Okay, now my pin's not working. Okay, there we go. All right, so this is, what did this turn out to be? What, 2 point?
3125.
Okay. 2.3125.
Yeah.
All right, good. 3125. So down in here, we got area times that 2.3125. And that gives us that static moment of area. So let's see what we come up with there. I'm going to get a number. You guys verify this. I got 16.043 basically. That sound right? .043. So now that we have that, we can solve this using the equation shear times the static moment of area divided by moment of inertia times B. So shear is 500. Static moment of area is 16.043 divided by I, which was from the table. We looked that up. B is the distance of the cross section along the neutral axis. Okay, so it's down here at the neutral axis, which is 1 1/2. Let's see what we get. We should get the same number that we already did. Let's see. We get 54.1 psi. You guys agree with that? we getting these values, guys? Anybody?
Yeah, that's what I got.
Okay. Which would you rather use, Erwin? This equation or that equation?
Wait, which ones again?
Which equation would you rather use? The 3v over 2a or the vq over iv?
Would it be the smaller number?
No, which equation would you rather use?
Oh, which equation? The 16.043.
I would rather use this equation. It's a heck of a lot easier. Okay.
Okay.
I mean, in order to get this right, you have to get Q correct. Okay. Q's the hard guy. Now, if you don't have a rectangle, you can't use this equation. Okay. So this only works when you have a rectangular section. All right. So what I guess my point is here, try to use this equation if you can, because it's simpler. Okay. This one here. But if you have a weird shaped cross section, you can't use this. Okay, you have to use that. Then
So the second one works for pretty much anything.
it works for everything. Okay.
Oh, okay.
Yeah, but if you have a rectangular cross section, Max, you can just jump right into this guy. It's a lot
Got it.
simpler. Okay.
Mm-hmm.
So that's the thing to keep in mind here. But be careful. Don't use this all the time. Okay, because it won't work all the time. All right.
Makes sense.
So that was really kind of part of the deck project right there. Now there's another one they want you to do for the other thing. I'll let you finish that one off, okay, on your own. Okay, any other questions out of 12? Before we jump over into combined stress stuff? Anybody want to look at? Keep in mind, we'll have time next Thursday also to look at some stuff, so. No problems that you can think of right now? Well, okay, I'm going to jump over to the PowerPoint stuff. I want to finish off a couple things. Has anybody tried any of the problems out of chapter 13 yet? Combined stress, where you have bending stress and shear stress considered together? Or the bending and the, not bending, not shear stress, normal stress? Anybody try any of those problems yet? No? You guys are not very responsive today. Okay, well, we're going to move on then. I'm not getting any response, so. I want to take a look at, last week we looked at combined axial and bending stress. Okay, so let's just, I'm going to buzz through that real quick, and then we're going to get into this thing called eccentric loads. And I'll do a problem or two, and we'll see if there's any other questions, okay? All right, let's see. So last week we talked about the concept of you have two things going on, the bending axial and bending and axial stresses. So we looked at that. What we want to look at today is eccentric loading. Okay, so just briefly, the one thing we want to note is that you know, there's more than one stress kind of going on. Actually, you can have bending, axial, and shear stress going on. Instead of looking at those individually, you can look at those all together. And that's what this kind of concept is going on with. So being able to recognize that and calculate that's important, because what you'll find is the stresses that occur at the top of the beam may not be the same at the bottom due to the fact that you've got these two types of stresses combined. So we have what's called a normal stress, which is the stress that's acting normal to your plane. And then you have the shear stress, which is the stress parallel to the plane. And so that what that means is your area is occurring in that direction. Okay, so we've kind of looked at that. So axial stress is really simple. You can solve that primarily as a force divided by cross-sectional area, so whatever your resisting area is. And bending stress is simply the MC over I. So by adding those two guys, in other words, solving the one and then adding it to the other, that's that process of what they call superpositioning, allowing you to look at the effect of bending stress and the effect of axial stress together through that process of superposition. So what you're essentially saying is I can solve my axial stress, and if this is, let's say, going in tension in this way, and my bending stress, because it's like a normal depth section, it's compression at the top and tension on the bottom. When I add these two together, I can get a combined stress. And in this case, it's showing me everything is tension, both top and bottom. That's not always true, but this is the concept of superpositioning. So essentially all you're saying is that your combined stress is going to be the combination of your axial stress plus your bending stress. So we looked at that last week. Okay. So bending stress, remember, is going to vary from 0 at the neutral axis to max at the edge fiber. That's true for both compression and tension. Now your axial stress is either going to be a tension stress or a compression stress. So we're going to have to assume signs on those. Normally, remember, we assume tension is a positive stress and compression is a negative stress. So we'll look at a problem doing that. Okay, and then this was just the steps that we went through. So I think I did one or two of these on the board. I'll do one of these. I'll do one of these today too, just to reiterate that. So what we want to take a look at now is due to what's called an eccentric load. So an eccentric load is when your load is not acting right down through the middle of your cross section, if you will. It's off to one side or the other. So what's happening is we're getting a load that's occurring off to the side, so that you're getting a moment that's being produced when you have an eccentric load. So you're going to have a secondary bending stress perhaps due to that. So you may have two moments, one due to the load itself on a beam, and then one due to the fact that you've got an eccentric load coming. So you end up maybe having an axial stress and then two bending stresses. So it depends on what your loading is. But this is an example of a case where you would have an eccentric load on this column, and you notice there is a eccentric load right here. Okay, so in other words, this load is not coming right through the middle of that. All right, so it's offset by E, which is your eccentricity value. And notice distance times force is going to produce this bending moment. Okay, so you get this. So you have a normal stress here. Okay, you have a normal stress. And then you have a bending stress, which is producing a moment. Okay, so this would be your axial stress calculation. This would be your bending stress, and what you get is this is your combined stress. Okay, so essentially, it's a common case where you may have, for instance, a column that is loaded eccentrically. Column might not carry the axial load right in the middle, okay? But it's going to be resisted by compressive stress as a normal stress here, force over cross-sectional area. But then because that load is applied not in the center of the column, it causes bending about that shape's neutral axis. So the moment that you get is developed as m is equal to your force divided or times your eccentricity. So that's just the distance off of the neutral axis area. Okay, so your bending stress is then calculated by utilizing mc over I, which really just develops to P times E times C. Okay, so we just have to deal with that. So we just solve an extra moment is what we come down to doing. So what they call a pre-stressed beam is what they call a real world example of where you would see this kind of thing with an eccentric loads. I'm going to do two types of problems. I'm going to do one kind of a column loading one, and then we're going to take a look at what we call this pre-stressed kind of beam. But what they do in these pre-stressed, they're manufactured with tension cables or tendons that are under compression. And then in the form, they put these cables in there, and then they pour the concrete around them, and then they release it, and it produces a bending moment in the beam. And that bending moment is referred to as camber or bowing. So this beam is already under stress, and then they just bring it in and lay it into its supports. So they use these a lot on bridges and those kind of things. Okay, that's where you'll see those. All right, so let's take a look at a couple of examples of this. Okay, so it's actually not that big of a deal to do. I'm going to do a couple of problems here. We're going to have a concrete column. Let me draw this picture a minute. So I'm going to have a concrete column that's loaded. Like, there's my concrete column, and I'm going to try to draw this represents the center of this column, okay, as best as I can do it. And we're going to have a load coming down over here off to the side. So the load is not right in the center, okay? So let me put the load value down. So we have a load value like this. And this point, that right there is my eccentricity. And so this is going to be 3 inches this way, okay? So this column has a value across it. This would be 12 inches here. Now I'm going to draw another diagram that would be looking down on this, okay? So let me draw a diagram looking down on. So let's say we're going to have looking down on this cross section. That would be looking in plan view. What we're seeing here is that this is, whoops, I don't know what I did there. All right. Well, I just did something. Okay. Oh, geez. Hold on a minute, guys. I don't know what I did. All right. All right, so this is 12 inches looking down on this way. And this column is 8 inches this way. Now my centroid on this thing is this way, and my force is sitting over here. Okay.
It's not showing the whiteboard.
Yeah, I can't see
It's
it
not
either.
showing the whiteboard. Okay, I did something. Hold on a minute. I do not know what I did. It says it's recording the session. Sharing the screen. Is it sharing that now?
Yeah.
Yeah. Now
Okay.
it's visible.
I don't know what I did. Okay. All right. What did you not see where I started? Let me back it up. Let me back this up. All right. Apologize. I don't know what happened there. Technology is great when it works, right? All right. So
Oh, yeah.
this is my column. All right. This is my column. We're loading it straight down vertically with a force. I didn't put a force there. So this force, we'll call that, dang it. We'll call this force P. That's 24,000 pounds. Okay, now note that it's offset by 3 inches. Now, if we look down on this thing, if we look down on this in plan view, what you're seeing is that this face is 12 inches on the column. This piece is 8 inches, which we can't see because it's coming at us. So the neutral axis here is right here. That's my neutral axis. And my force is coming down right there, which is located 3 inches off of the neutral axis. Does everybody see what I'm getting at now? So because this thing is like that, there's a moment happening here. It's putting this in tension on this face. So this will be in tension and this will be in compression over here. So that's going to be in compression and that's going to be in tension due to the moment. Does everybody understand what I'm getting at there? Do you guys see that? If there's a moment happening here, it's tending to pull up this way and push this way. So the moment's like this. It's a clockwise moment. It's putting that edge on tension, that edge on tension, and this edge is in compression. You guys see that?
Yeah.
Okay. So we have two stresses going on here, guys. Two stresses. We have a normal stress, which is just simply force divided by cross-sectional area. So this is compressing, so this will be a compressive stress. So we're going to consider compression negative. So the force is 24,000 pounds divided by the area, which is going to be what? 12 times 8. And that'll put it in PSI, okay? You guys agree with that? What did you get for the compression? Looks like, did I do that right? See if you got that number. (250 PSI).
Yeah, that's what I got.
Now, is it compression or is it a compressive stress, Max, or is it a tensile stress? So this force is pushing right down on that column.
So it's compression.
Right, so we're going to consider this a negative stress because we're going to consider compression negative. You agree?
Yeah.
Okay, so now we have a bending moment. So remember, the moment is going to be equal to P times E. So P is 24,000 pounds times the offset distance, which is 3 inches, right? So that moment is 24,000 times 3, gets me 72,000. And what would the unit of that be? Inch pounds. Inch pounds. You agree with that?
Yeah.
Okay, so bending stress is equal to MC over I. Okay, so we know what the moment is, right? What is C in this picture? The distance from what? Neutral axis to the edge fiber, correct? Neutral axis to the edge. So what would C be?
Is it 6?
It's 6. It's exactly 6, correct. Now, So we know what M is, right? M is 72,000 inch-pounds times C, which is 6. What is I? Be careful on this. What would I be? 1/12 the base times the height. Which is the base? 12 or 8?
It's got to be 8, right?
Yeah, because base is always parallel to the neutral axis, right?
Yeah.
Okay, so this would be 8 times 12 cubed. You see how you could confuse that really easily?
Oh, for sure.
You
Yeah.
have to be really careful then, okay? All right, so that's 1/12 the base times the height cubed. Let's see what we come up with that, and that'll give us our bending moment. So we have, let's see, 8 times 12 cubed divided by 12. I'm going to just calculate the whole thing and see what you guys come up with. We'll compare them. Ooh, that didn't work. You guys let me know what you get. I get 375 PSI due to the bending.
Yeah, that's what I got too.
You guys agree? Now let's think about this. This would tend to be both positive and negative, right? It's going to be positive at the back of this. It's going to be negative at the front because it's tensioning, compressing. Tension, compression due to the way that moment's occurring, right? So we can set up a chart. If we call this the back and this the front of that column, we can say that the front and the back, we have a normal stress, we have a bending stress, and we're going to have a combined stress. So the normal stress is negative for both, front and back. That's a negative 250. Because whether you're front or back, that column's still in compression due to the normal stress. Or it developed as compressive stress, I guess I should say. All right, what's true about the bending stress on the front? That's compression, right? So we're going to add to that a negative 375. So when we add that,
When you're adding compression, it's always going to be negative, right?
well, let's just qualify that. You can call compression negative or positive. It doesn't matter as long as you're consistent, okay?
Okay.
So the way I always do it and the way the book always does it, I always consider tensile stress is positive and compressive stress is negative, okay?
And
But I'm adding these. Go
what
ahead.
is tensile stress?
Say that again.
Tensile stress or tensile? What's the difference? I'm sorry.
What's the difference?
Yeah.
Well, one is because we have a compressive force going down here, right? We're developing a compressive stress. That's why this guy's negative here.
Okay, I see that.
But because of this moment that's happening, we got that bending moment going on there. We've got a bending stress developing here. It's tensioning the back fiber of that column, so it's going to develop a tensile stress to counteract it. And it's compressing the front of that column due to this moment. So the stress in the front is going to be developed as a negative bending stress. Okay?
Okay, I see now. It's kind of like to look at the shape more like malleable rather than like fixed.
Yeah, I mean, yeah, you can think of that, but just what you really need to think about, remember, stress is not a force, number one. It's what's developing within the material so that it resists that force, right?
Yeah.
Okay. So the force, you can look at it this way too. The force here would be a tension force, and the force here would be a compressive force. But the compression across the cross section is just straight compression. That's why this guy just has one sign, positive or negative. Okay.
Gotcha.
But this guy, due to the fact of the bending moment, how it's occurring, it's going to be positive and negative. Does that help?
Yeah, signage is important.
Yes, definitely. No, definitely. That's absolutely true. So when we sum them, right, we're going to sum those algebraically, and we get a negative 625. We really don't have negative stress. What we have is what? A compressive stress. But we're just using that to indicate that we've got compression. Okay.
Gotcha.
In the back of that column is in tension due to the bending. So this is a plus. So when we add those, what do we come up with?
Should be 125, right?
I think so. Yep, a positive 125.
Yeah, because the 375 is greater than the negative.
Right, so what's happening is the back of that is still in a bit of tension, developing tension stress, and the front is major compression. Does that make sense?
For sure, yeah.
Now, let me clean this up a minute. We're gonna take a look at what I would call a pressure diagram of what's happening with your stresses. So can I erase this stuff right here? I'm gonna go ahead and erase this. And that as well. Okay, so if I diagrammed that stress, okay, I'm gonna make it a little diagram. I have, let's say, a zero load. Let me draw a little axis here. So I have a zero axis line. This represents zero stress. I'll put tension on the top, compression on the bottom. So if we look at this, this is a linear relationship, okay, where this guy has a maximum occur. This represents 625. This represents a tensile stress of 125. Notice that if this is the centroid of that, right there, the center, this would be 6 and 6. This is not coming through the centroid, so you don't have zero stress developing at the centroid. It's to the left of it or to the right of it. Do you guys see that? And this is linear, so we could solve the stress at any point we wanted to by using the slope of that line. Okay, where this is your tensile, this is your compressive, and that point would be zero stress. But it's not at the neutral axis. In this case, it's to that side of the neutral axis. This being my neutral axis here. You guys see what's going on with that? That's what's typically going to happen with these types of problems. You guys get the idea on that one?
I definitely think without the diagrams, it would be a lot more confusing.
Well, you have to. I mean, everybody uses. I mean, yeah. You need the diagram for sure. Okay, and you have to look at. You kind of have to think maybe two directions. You know what I'm saying? You have to think about being in two directions. All right. Let's do one more problem, okay? Yeah, we'll take a look at this one. And let's see what I need to do here. Give me a sec, I gotta get a problem developed. All right, let me clean this up. You guys still see everything okay?
Yeah.
Yeah.
Okay. All right. So I'm gonna give you a beam problem. So we're gonna have to work through the statics on this first, but let me give you the situation. So we have a simply supported beam. So it's got a support here, and it's got a support here. All right. This thing has a uniform loading on it. So it's got, you know, the arrows. This represents a uniform load rate, okay? And that load rate is 3 kips per foot, okay? So we have a support here, we have a support here. Now, in the cross section, well, let me do this. We are loading this. We're going to be loading this, let's see, with, we're going to load this actually down here also with a, we're putting this in another force that's coming in this way. Now it's balanced, but it happens to be below the neutral axis. Okay, so this is an 80,000 pound compressive force. So this thing is put in a compression. This is what we're talking about doing with those beams. If I draw this in cross section, is what we're going to look at in a cross section. Okay, so this is the cross section. This is the neutral axis of that beam. Down below that neutral axis, I have cables running through it, okay? And those cables are the thing that's tensioning this, or compressing this rather, but they're not coming through the cross section or the neutral axis. They're 4 inches below it. So this is my neutral axis here, and these cables, that's this guy, these are 4 inches below. This cross section on this beam is 12 inches by 20, so we're going to have 10 inches here above and 10 inches here below. So the depth on that, it's actually a 20 by 12 inch beam, okay? Does everybody get the idea? Is everybody okay with that? So this one's convoluted because we have 2 bending moments going on here. We're going to have a bending moment due to this beam being in loading this way. We're going to have another bending moment because this guy's going to put a bending moment like that on it, okay? So we're going to have 2 things going on here. All right, so the first thing we need to do is figure out what is the bending moment of the beam itself. So we're going to run through some statics here. We got to do a shear moment diagram on this thing. So sum of forces in the X equals 0 because 80,000 and 80,000, that's 0, okay? Sum of forces in the Y, if we call this A and we call this B, oh, I need to know one more thing. I forgot to put that down. This is a 20-foot span, okay? So we have the reaction of A plus the reaction of B has to equal 20 times 3. What does that give us? 20 times 3. $60 kips. So that has to equal 60 kips. So can we say anything about the reactions here? Acting vertically? Anybody have an idea? Is this symmetrically loaded? Got a uniform load rate across the whole beam. So is that symmetrically loaded?
Yes.
Essentially, yes, right? So what does that tell us about this reaction here and here?
They should theoretically be the same.
Yeah. Okay, so if we wanted to prove that, we could do a moment real quick, right? So let's just do a real moment just to verify that. I'm going to take a moment at A. My 60 kips is acting in the middle of that beam, so that would be 10 times 60. Whoops, hold on a minute. It's 10 times 60, that's a plus moment, minus 20 times RB is equal 0. So that gets us 600, comes over as a negative 600. Negative 600 divided by a negative 20 gives us what? 30 kips, just like we said, right? So we can now say that this guy has got 30 kips on either end. So we've got 30 kips of sustained load here and 30 kips over here. I'm going to go ahead. We okay with that? Everybody good?
Yeah.
Okay, I'm going to go ahead and erase this because we're going to need that room. So I'm going to get rid of that. So we need to do a shear moment diagram. Okay, so critical lines are developing where? One here, right? Whoops. There's a critical line. Where's the other critical line? Right here, right? Any other critical lines? Do we have any other point load forces up here? We don't, do we?
No.
So we're going to have a shear, and we're going to also have a moment develop. Because we have to deal with bending moment on this problem, we have to actually solve the bending moment on this, okay? So we start out with the left side. What's the amount of shear on the left side? It's coming up at 30 kips, right?
Yeah.
What's happening as we step across that beam? Staying
It's going
constant.
down.
It's going down. And it's going to go down what? At a rate of 30 or 3 times 20. So that's going to give us a negative 60. So what's happening there is this guy is stepping down at that 30 time or 3 times 20 rate, brings us down to a negative 30. So we have negative 30. Negative 30 plus 30 goes back to 0. So we're good with our reactions, correct? And this is shear, right? So what we need is moment to be able to determine the bending moment on this guy, okay? We want the bending moment on that. All right, so we have a 0 line that has our 0 point of shear. Where is that 0 point of shear occurring? Where's the 0 point of shear?
At the middle.
Right at the middle. Yeah, so we know that that's 10 over. That's correct. So this is 10 and that's 10. So we have a maximum moment that occurs there, right? So we got area 1 and area 2. So we're going to start out at 0. Since this is diagonal, I know that I'm going to be going up parabolically. And then this has to then come back down parabolically. And it has to go to 0, right? So the moment of 1 is going to be area of 1, which is going to be 30 times 10 times 1/2. 30 times 10 times 1/2 gives me 150 kip feet. Okay, 150 kip feet. So this is at 150. And then the moment at 2 has to be equal to 0. So that's going to be the moment at 1 plus area 2, which is negative 30 times 10 times 1/2. And that goes to 0 and that checks. Okay, is everybody all right with that? We good on that?
Seems pretty straightforward.
Say that again.
Seems pretty straightforward for the most part.
It is. I mean, that's nothing new, right? Now, we haven't even looked at what's going on here yet with the cables below. We're going to get to that in a minute, okay? But we had to solve this to get what's going on this beam. So we have a bending moment going like this. So that's putting the top of that beam in compression and the bottom in tension, okay? Is everybody okay with that? The bending moment of this, due to this situation of the loading, is we're putting compression on the top, tension on the bottom, okay? Is everybody okay with that? So I'm going to, what I want to now do is calculate the bending moment due to the load, okay? So I'm going to clean this up. We don't need that anymore. We're good with that. So we can calculate bending moment. Oops. We can calculate bending moment due to the load. We'll call this bending 1. Okay, so this is bending 1. So that's equal to MC over I. So it looks like we need to calculate I. Let's go ahead and calculate that separately, and then we can plug that in, because we're going to need that several times. So there's my neutral axis, and this is the base. So that's going to be 12 times 20 cubed divided by 12, which really just turns out to be 20 cubed, it looks like. Looks like 8,000 inches to the 4th. Okay. So for the bending due to the load, we have 150 kip feet, but we need to convert that to what?
You divide it by 12 to make it into inches.
Did you say divide it by 12?
Or you multiply it by 12, sorry.
Are you sure? Do we need to look at that? Should we look at that?
I'm confused.
Okay. 150 kip feet times how many inches per foot?
12.
So we want 12 inches on the top, right? And feet on the bottom, so they cancel. So we're multiplying by 12. You agree now?
Yes, yes.
Oh, okay.
Got a little mixed up there.
Do not hesitate to do that if you need to, okay? Because
definitely,
that's a really common mistake. I mean, I make that mistake myself sometimes. You've got to watch that, okay? So C is the distance from the neutral axis to the edge fiber. So what would that be? if it's 20 depth and the neutral axis is here, it's going to be 10. I is 8,000. We just calculated that. Did you guys get that, by the way? Did anybody check that 8,000 number? Anybody get that for the I?
Yeah, I got that.
Okay. So let's see what we come up with then for our bending stress due to the load. What'd you get?
I got 2.25.
What would be the unit of that?
Inches. Oh, wait, no.
Well, we're kips, right?
Yeah.
Kip feet?
Yeah.
Or kip KSI in that rather, KSI, because everything that's in inches, that's kip inches and that's inches to the fourth, so it's KSI. Okay. Yeah, 2.25. Now, if you wanted to convert that to pounds, which we have to be careful because this guy's, remember, this guy is in pounds. I forgot to note that that's in pounds. So we have to be careful with our units, okay?
Yep.
All right, so what's true about this? Is this compression? Is it tension? Is it both? Remember, this is what the moment's doing on the beam being loaded this way. So with compression, tension, what's going on there?
Is it compression?
It's both. It's going to be compression at the top because it's compressing the beam down, but in the bottom, the beam's reacting by elongating, so it's under tension, okay?
Okay.
So we're going to consider this positive and negative, okay? Keep that in mind, all right? Everybody okay with that?
Yeah.
All right, so let's look at the normal stress on this cross section. Normal stress is this compression. Normal stress is simply P divided by A, okay? So the force on this normal stress is this 80,000 pounds, but if we convert that 80,000 pounds to kips, what would that be in terms of kips? 80,000 divided by 1,000 gives us 80 kips. Our cross-sectional area is simply going to be 12 times 20. I got 0.333 KSI. Anybody get that number? Anybody get that number?
Yeah, I got 1/3, but that, yeah, 3.
Okay. Now, let me ask you this, Mitch. Is this a compression, tension, or can it be both?
I think it's just compression.
You're absolutely right. So this is considered a negative because this thing is, we're looking at the stress that's developing in this axis right here, okay? So it's pure compression. So this is not going to be both. So that means the bottom fiber is under compression and the top fiber is under compression due to that force. So therefore the stress that's developed is compression as well, okay? You guys okay with that? So we have one more bending stress to develop. The bending stress due to the fact that these cables are below the neutral axis, so they're compressing the bottom fiber and tensioning the top. And we're using this equation now, MC over I, but I is going to be the force times the eccentricity times C divided by I. So what is the force here? It's the 80,000 pounds, which we said was what? 80 kips, correct? E is the distance above or below the neutral axis. In this case, it's below. So it's below by 4 inches. So this has been tensioned, well, it's been compressed by that. And then what is C? C is the distance to the neutral axis, from the neutral axis to the edge fiber. So that's going to be also 10. Divided by that cross-sectional area. Let's see what we come up with there. I get 0.0 or 0.4 KSI. Anybody getting that number? Point 0.4 KSI. Are we okay?
Yeah.
All right, so we're gonna do a little chart. We're gonna call this chart the top. Whoops, that's not gonna work. We're gonna have the top and the bottom, and we're gonna look at the compression and the tension. So we have a normal stress, top, bottom. We have bending stress 1. We have bending stress 2. And then we're going to have the combined stress. So what's true about the top and the bottom under the normal stress? We said that that's all negative, right? It's all compression. So we have a compressive stress, top and bottom. Does everybody agree with that? Bending 1. Bending 1, let's look at that a minute. What do we say is happening due to the stress or the moment at the top fiber? Pushing this way, it's compressing the top and tensioning the bottom. So this guy is going to be a negative at the top, compression, and a tension at the bottom. You guys see that? Because this moment is turning like that, it's compressing top, tensioning bottom. So top is negative, compression, okay? This guy is also going to be a plus or minus, but it's compressing in the bottom and tensioning on the top because it's turning this way, because this guy is below the neutral axis. If it was above the neutral axis, that moment would be going the other direction. So it's compressing the bottom by 0.4, and it's tensioning the top by 0.4 KSI. So when we add these guys together, that's going to be your combined stress. I get a negative 2.183 KSI. So what that's telling me that that top is in compression. If we add the bottom, we get a positive 1.517 KSI. So the top of that beam is in compression, and it's developing a compressive stress at the top. The bottom of that beam is in tension. So it's developing that tensile stress. You guys okay with that?
Yeah.
All right, so I'm going to do a pressure diagram real quick, and we're going to determine where the 0 point of stress is. Okay, I want to determine 0 stress. So I'm going to delete this, delete that. Okay, so give me let's see, let's draw a little diagram here. So if we looked at this beam on edge, and let's say this is the neutral axis coming through there. We've got compression like this, and tension, which is a lot less. So notice what's going on there is that. So this is compression, 2.183. This is tension at 1.517. You can see this is the neutral axis. So the point of 0 is going to be below. So what would that distance be? Let's see if we can solve that. So we basically have a similar triangle, which would be that side, that plus that added over this distance. So if you add the 2.183 plus the 1.517, so I'm just looking at absolute values here. I'm not looking at sign. So I get 3.7 is to a distance of 20 inches, as this, we'll call this X. X is to a distance of, whoops, I got that reversed. Hold on a minute. As 1.517 is to a distance X. Solving X, you get what? Okay, so I get a value of 8.2 inches. So what that's saying, we know that the neutral axis is at 10 inches up. This is below it, and it's from that edge up, it's 8.2 inches, which makes sense from our diagram. Okay. This is what you would call a post-tensioned or a pre-tensioned type of pre-stressed concrete. A lot of times they use that term, pre-stressed concrete beam. And these are used quite often because they can be manufactured and then just brought out on the job and put into place. And so it already has that combined, that stress involved in it. And then when it loads, it helps overcome that. Any questions on that? There's a lot to it. The biggest thing you have to watch on this, it's not too terribly bad, but you have to think about the sign of your bending stresses. The normal stress, it's pretty straightforward. It's either in compression or it's in tension. Okay. So same thing there. All right, any questions? Because that's kind of all I had today. Any questions on the problems? Any questions on the DAC thing?
Not that I even think of.
Okay. Well, I will be around pretty much all week, and we'll do another lecture next week talking about Morse circle on Tuesday. And that is going to finish up chapter 13. So what I would like you guys to do over the next couple days, if you can, first off, taking some time and enjoy it. And secondly, work on that deck stuff. I want to get that done a week from Thursday, turn it in. And we're going to finish up problems out of chapter 13. So if you have any questions out of 11, 12, or 13, shoot me an email. We can do a Zoom session. We'll finish up on next Tuesday and do some stuff on that Thursday, and then we'll have our final the following week. Okay. Any questions then?
No.
All right, guys. Well, enjoy your break, enjoy your holiday, stay safe, and I will see you next Tuesday then. I'm going to go ahead and I'll stop the recording, and then